afternoon to everybody. We are going to discuss a new technology for space communication that is based on transmission of optical signals. Space communication means basically satellites communication, and I'm going to spend a few minutes about a brief recall of what are satellites and what is the main use of satellites. As most of you know, satellites are autonomous vehicles that are orbiting around the Earth according to Kepler's law. And they are typically classified in terms of the orbits. We have low Earth orbits, medium Earth orbits, and geostationary satellites, LEO, MEO, and GEO. According to Kepler law, the speed of these satellites around the Earth is on the order of kilometers per second. So it's quite impressive, even if the relative speed, for instance, for GEO can be considered almost zero. Why do we use satellites? We use satellites today for many purposes. First of all, navigation. Everybody is familiar with GPS, but we use also a lot satellites for monitoring, to monitor pollution, water, commercial routes, but also for emergency conditions. And finally, we use satellites for communications. Actually, around 1% of long distance data is carried out by satellites. On top of that, you have to add a lot of data transmission, which is referred to data that are generated by satellites. For instance, the satellites that I mentioned before that carry out monitoring. This trend of using satellites for communication has seen a recent increase, quite a sharp increase, thanks to Starlinks by SpaceX, which everybody should be familiar with. I don't need to explain too much about this topic. And I want just to mention that Starlink is not the only one who is using or planning to use satellites for communication, because there are also other relevant players, such as Eutelsat, for instance, or I2 to come soon. Note, this is a key warning, the type of communication that we are going to discuss today and that is presently deployed and will be deployed in the near future is completely different in terms of capacity with respect to the internet backbone that is implemented using optical fibers. Transoceanic links can carry up to 200 terabit per second per link. This is by far a figure that cannot be reached using space communication. Space communications are still relevant. There is a lot of attention also about strategic activities due also to current geopolitical conditions. You know, here there are some recent news about the fact that satellites are typically used for monitoring other nations or other nation armed forces. There is a specific network to monitor nuclear attacks, for instance. There is, on the other side, presently no evidence of any orbital weapons actually deployed. But for instance, hyperspectral monitoring is a powerful solution that allows you to look even through clouds to monitor the condition of strategically important activities. Now, after this short introduction about satellites, let's have a look at how many satellites are deployed. This is a graph that I produced based on available data. This is the trend of the number of satellites versus year. And you can see there is a sharp increase after year 2020. And this is not just an increase in the number of satellites, there is also a sudden increase in terms of data volumes that satellites are going to transfer. For instance, it is expected that we will see an increase by 14 times in the next decade of the data that are carried out by satellites. So this means that we need faster speed, and likely this requires new technologies. Fast speed means higher than gigabit per second, and this is a limit that current radio frequency systems have problems to reach. Finally, said that we are going to have a network of satellites and a lot of communications involving satellites. Let's see what type of links we expect to realize in the near future, and partly even a part of these links is already in place today. There are, first of all, inter-satellite links. That means links connecting in point-to-point condition in satellites that can be either in the same constellation. If you see the mouse pointer here, you should see. But also satellite links that connect satellites that are presently in different constellations. Constellation is one of those lines, basically a trajectory over a given plane where different satellites are moving around the Earth. So inter-satellite links allow different satellites in the same constellation or in different constellation to exchange data at fast speed. Of course, this is not enough. You also expect to have feeder links, which means links that connect either downlink or uplink the Earth with one or more satellites. And you understand that from a physical point of view, these type of links have different features. Inter-satellite links are related to objects that are moving very fast, especially if they belong to different constellations. The relative speed can be quite high. Whilst the feeder links would be in principle simpler from the point of view of pointing the signal beam, but they face a huge problem related to the impairments that are due to the passing of signals through the atmosphere. So either downlink and uplink in this case will pass through the atmosphere and as such can suffer from relevant impairments. So how can we produce high-speed transmission? In general, in communication, higher speed asks for higher carrier frequency. But there is also another feature of long-distance communication that is relevant. That is, electromagnetic waves tend to spread when they propagate in free space, and this spreading is related to the carrier frequency. And actually, it is by far faster at radio frequency than in the infrared region. Here you can see a picture. This is the Earth. And the red circle you can see is a circle that is corresponding to the illuminated area from an antenna on the moon using radio frequency. In the center of the circle, a green dot you can see here. The green area is representing the area that is illuminated by a similar antenna with the same diameter but emitting optical radiation that is in the infrared region. You can see that there are two key features. The illumination cone is, of course, much smaller. This requires higher accuracy in the pointing, but on the other side, the fact that you have such a small area compared to the red one gives you much higher intensity, which allows you better signal to noise ratio and higher bit rate. Note that this is a problem for all long distance space communication, and this is, for instance, a big problem if you go into what is called the deep space. For instance, NASA has estimated that transmitting a Google Maps with just 1 bit per pixel resolution with the best radio frequency signal would take around 9 years, which is a huge amount of time, as you can understand. So this consideration, the need for high frequency, and the fact that you need a beam that does not spread around fast, move the attention to the optical frequencies. And this is not just a speculation. There have been several demonstrations. The first one that is noteworthy is a hero demonstration that took place in 2013 with the lunar laser communication demonstration. NASA was able to transmit down to Earth a signal at 600 megabits per second from the moon. It was, of course, enabled by key devices that we cannot cover in this talk, but is a relevant piece of technology that was instrumental to reach this result. Before going ahead, I would like to take a step back, because my group, 15 years ago, we have demonstrated the first 1.28 terabit per second system over a terrestrial link. It was the first WDM free space optical link at such high speed, but in general, it was the first WDM free space optical link. A key point was to use transparent terminals that you can see here, and those terminals could be connected transparently to optical fibers in such a way that the free space looks like a seamless extension of the fiber itself. Here you can see a picture of the demonstration that took place 15 years ago, connecting the roof of 2 buildings in our campus. This is the roof of Scuola Superiore Sant'Anna building, and this is roof of another building. And we were able to transmit 32 wavelengths, each one modulated at 40 gigabit per second, back and forth. The key point of this demonstration is that you can reach such a high wireless capacity by simply using existing devices, which are reported here. So you use the FP laser, you use modulators, you use amplifiers, WDM multiplexer, filters, photodiodes, and everything that is already a component used in fiber networks. So here are some results that I can skip because of time limitation. One important feature from this type of experiment is that over a long period of time, the bit error ratio was always, almost always good, but in some cases we have seen spikes of errors that you can see here. And this is a feature that we will come back later. These type of systems have an intrinsic outage probability which is not zero. Whatever you try to do to make these systems properly designed, you will always have an outage probability which cannot be neglected. So from these hero experiments, people after 15 years are thinking about using the same concept to produce WDM free space optical system for satellite communication. Here is a pictorial view from one of our most recent papers. Here you can see a downlink signal in light blue, an orange signal which is uplink to the satellite, a red signal which is an inter-satellite link, and we also have a deep space link in green. So the idea is that you can create a mesh of optical links using this technology. And the key point is that thanks to transparent terminals, you are able to reuse most of the technology that is already in place from fiber network communication. This means that space communication, optical space communication, are moving from the old proposal of sorry, 1064 nanometers to the new region, which is the C-band, that is 1550 nanometers. There are a number of positive facts about this, which is you leverage upon 40 years of research and development. As I said, you have a lot of systems, subsystems, and devices which are already available. Your signal has the highest directivity. In principle, you can have very small antennas, and you can have a potential speed of hundreds of gigabit, even terabit per second. Unfortunately, you have also some problems, and those problems are listed here. You have an extreme need for accurate pointing. Since the beam divergence is so low, you need to point the beam properly. And this may not be simple if you consider that satellites are traveling fast. You have a turbulence effect, which we will come back later. And then you have sensitivity to rain and fog. And finally, not all the hardware that you need is available. You will need, for instance, telescope and adaptive optics. Again, this will be discussed in the next few slides. So let's come back to the type of links and consider the specific issues that you have due to optical wireless communication. So in inter-satellite condition, you have these satellites moving fast, and the key issue is pointing, alignment, and tracking. This is critically, especially if you think about inter-constellation links. Then you have the feeder links. Feeder links can be characterized depending on the different distance, and typically also on the different speed. Different distance means different latency. So for some application, latency is an issue. And so, for instance, you will have to prefer LEO. But in other cases, you may need also better stability. Then you will possibly refer to GEO. Different speed. Typically today, people tend to trust more on LEO, and there have been demonstration of transmission, downlink transmission at 200 gigabit per second from LEO down to Earth. A key point in these feeder links, if you use optical signals, is atmospheric impairments. Atmospheric impairments are due to the atmosphere, mostly the first 10, 20 kilometers of atmosphere. And these will have a different impact in uplink and downlink. Typically, the atmosphere impact is much higher in uplink than in downlink. So here you can see in this slide an example of design system, a scheme of our system with different transmitters, multiplexer, a booster amplifier, a telescope, which is here indicated as a simple lens, but is not just a simple lens. Then you have a turbulent atmosphere, receiver, preamplifier, erbium doped fiber amplifier, then the multiplexing and receiver. As I said, the first issue is pointing and tracking. Why? in this condition, you need for this system to work that all the light will be focused properly on the fiber that is just after the receiver telescope, a fiber that has a few tens of microns of core diameter. And you can imagine the complexity of the pointing, alignment, and tracking mechanism that must take light coming from, for instance, a LEO satellite that is moving fast. It's 500 kilometer or higher altitude, and then collect the light and couple the light into an optical fiber. This is by far not simple. Then you have the issue of the channel. So the atmospheric, the effect of the atmosphere, which can be summarized in two categories: absorption and scattering, and then turbulence. And finally, the atmosphere impact that depends not only on the fact that you are a given path through the atmosphere, but also on the angle, because the total length of the path will depend on the altitude of the satellites, but also on the elevation angle, that is the angle of the apparent relative angle between satellite and vertical lines of the receiver. And finally, as I said, you have issues about fiber coupling. So this is an example of a spectrum of absorption and scattering. The interaction with molecules and aerosol particles in the atmosphere produce huge losses in some regions. This is typically deterministic and wavelength dependent. And you can see in the dashed light line the effect of Rayleigh scattering. And in green, you can see the area that we are going to use, that is the C-band. Luckily, this is a region where the transmittance is the highest. We have almost 1 dB of losses due to scattering, which is quite acceptable in these conditions. Much more important is the turbulence effect. We must say that the refractive index of atmosphere is not exactly 1. Pressure and temperature variation produce a random fluctuation in space and time of the refractive index. This is frequently indicated as eddies. And so these may look negligible if you just consider a path that is quite short. But if you consider the effect over 20 kilometers of atmosphere and then the propagation in free space to the satellite, you can see that even small refractive index fluctuation give non-negligible effects. The first direct consequence of refractive index not being constant is that the wavefront is modulated. Basically, the phase of the beam is modulated. Here you can see the signal coming with the wavefront, which is a plane wave, and then after passing through the atmosphere, the wavefront is distorted. This, for instance, creates problems to couple light into the single mode fiber that you have in front of the receiver. A signal made like this can have problems. Even more, you have problems when you go into uplink condition. Here you can see an example of what you get if you have a large scale fluctuation of the refractive index. Here you can see a scheme where we have just 2 eddies. They are quite larger than the beam. The result of light passing through these eddies is that it's moved around. This is a kind of random walk effect, and the result of that is that the beam is deflected. This is typically called the beam wander. Of course, you can have also eddies that have sides much lower than the beam width. those are small scale fluctuation and are indicated here in this picture. And you can see the presence of the small scale eddies tends to produce fluctuation of the intensity in the beam itself, and in the worst case, even what we call filamentation of the beam. That is the beam dividing in multiple bright spots. Both beam wonder and scintillation can be partly compensating by adaptive optics, as we will see now. What is adaptive optics? Adaptive optics is a key technology that was developed in physics for astronomy. It was used to compensate image flickering. The idea is that you have a light, which is here indicated as plane wave. This is distorted, as we have seen before. The light is collected by a telescope, and here part of the light is split to a wavefront sensor. The wavefront sensor basically measures the distortion of the wavefront, and through a control system changes the shape of a deformable mirror in such a way that the deformable mirror compensates the variation of the wavefront and produces a plane wavefront again. This is usually, it's naturally to be used in downlink because this was the original application for downlink. But in principle can be used also for uplink. There are a number of limitations, however, for uplink. In uplink, basically you sense the distortion of the wavefront in downlink and then apply the same predistortion to the uplink, assuming the two beams passing exactly through the same region of atmosphere. This is not always to be given for granted. And so that in the uplink, the pre-correction is not always perfect. Also note that the requirements of telecommunications are much different from those of astronomy. In astronomy, you take a picture of a far star. If the picture for some reason is not good, you take another picture. If the picture has an exposure time of 10 seconds and in 1 microsecond something is not working perfectly, you don't care. Telecommunication, you have much tight requirements. So you cannot think that if you do not receive data, you forget and try again, or at least this means automatic retransmission with a lot of different tools involved. And also you cannot expect that if you lose a signal for 1 millisecond, everything is fine because it's a minor part of your signal. So the technique is good, the principle can be used, but you need a lot of work to make it suitable for communication. Just to give you an example, this is an example of numerical simulation of uplink to a LEO in two different conditions. We talk about weak and strong turbulence condition when the effect of the atmosphere is limited. For instance, during the night, you have a weak turbulence typically. During the day, you have a strong turbulence. Here you can see there is some beam wonder. The beam has moved from the center of the grid, but here you can even see filamentation of the beam. So this can be compensated. This is much harder to compensate. You can do in principle. And in general, as I said, the effect of turbulence produces what we tend to call deep fading events. These are flat fading. They are not frequency selective. So basically your signal is disappearing. You have a statistical distribution of received intensity, and this is an example of time series. So sooner or later you will see a drop of the signal, received signal power, which is much lower than what you can tolerate. And so the signal will basically disappear. This is a complex topic that we are experimentally investigating here at Sant'Anna. I'm not going to spend too much to describe the results, but just to mention that the fiber equipment is not optimized to deal with this type of fading, statistical fading events, because in a fiber network, basically your signal is always present. If it disappears, it will never come back. It disappears only if you have, for instance, a fiber cut. The fiber will never recover. So what happens is that the equipment is not designed to deal with the fading that lasts, for instance, 10 milliseconds, and then the signal comes back again. This has a number of implications, because the equipment will have some recovery times that in many cases can be longer than the fading itself. Finally, another point that I want to touch briefly is the role of the telescope. Pointing error and beam wonder can basically assimilated, and because they are both referred to angular errors. One way to manage this is to have a beam which has a divergence typically greater than the beam wonder or the pointing error angle. This is possible, of course, but again, you can understand that if you have a higher divergence, you get lower intensity. So there is a trend to optimize, there is a need to optimize the transmitter and receiver diameters in such a way that you can obtain the best link power budget. Okay, I give you now just a simple example of a design that was carried out within ITA and TN, which is an initiative within the Restart project. This is a schematics of a network where you have a base station, smartphone, ships, and you have as terrestrial nodes, but you also have non-terrestrial nodes such as LEO, apps, geo satellites, and so on. And we have chosen a few links in this network for a common exercise with a comparative analysis in feeder links with different technology, with two objectives. One objective in terms of capacity, one short-term objective, and one long-term objective. And this is the summary of the exercise related just to free space optics. It was related to uplink condition because, as I said, uplink is the most stressing condition. And we have seen that, for instance, for different nodes in the networks, basically high altitude platforms, LEO satellites, and geo satellites, it is possible to transmit up to the long-term objective, 100 gigabit in the case of apps and LEO, and 10 gigabit per second, which is the case of geo satellites, according to, let's say, some practical parameters, antenna diameters on the order of less than 20 centimeters, both on ground and on board, which is important because the fact that you can use a small antenna is instrumental, especially if you have small satellites. You have, of course, a very limited amount of pointing error, which is on the order of few microrads, and this is an issue that requires a significant technological effort. And finally, a range of transmitted power which is almost compatible with what you have today in fiber network. Okay, I can be very quick on this. This is representing the type of devices that we have in fiber networks that we can use. And I want to outline, among other subsystems that I've mentioned before, that we can also leverage upon the coherent detection scheme based on fast digital signal processing in ASIC. This has been a key technology to reach 100 gigabit per second over a single wavelength in fiber networks, and today is used to reach much more than 100 gigabit, up to 800 gigabit per second. But coherent detection enabled by DSP is also a key technology for space communication. And the big advantage is that this technology you can use basically for free, because you simply use the transceiver that were designed for a different application and move to the space domain. Okay. Said like this, you can expect that almost everything is done. There is a lot of things that still need research and industrial effort. There are some missing devices and techniques. Among those, the adaptive optics with suitable performances, high power amplifiers, and suitable pointing, acquisition, and tracking, and some other that are limited in this presentation we are not going to touch. Then one key issue is to test space-grade technologies, because we have the big benefit to take these technologies from fiber communications, but we are not completely sure that exactly the same devices can work in the space. Of course, on the optical ground station, which is on Earth, everything is fine. But you have to consider that the typical space condition in terms of acceleration, temperature, and radiation can be quite different from those that were assumed when those devices and subsystems were realized. Finally, also you have to consider how you can manage the fadings. There is a lot of discussion about this. There are solutions, for instance, based on automatic retransmission requests, but this, of course, has an impact on latency. There are other alternatives which we are exploring that requires more sophisticated solution. And finally, you have to deal with the networking issues. The first of them is rerouting. If you have a link which is not working, and I have explained to you a number of effects that can make a link not working, then you have to reroute the signal, which involves complex strategies. So at this point, you may ask, okay, you have made a nice picture, but it seems you have a lot of issues with all these kind of pencil beams moving around, satellites traveling a kilometer per second, passing through the atmosphere, pointing, aligning, and tracking, and so on. So you may say, I don't believe it. Okay. Here are some evidences that something can be done. Pieces of news taken from common website. SpaceX achieved laser data transmission. NASA has demonstrated that a CubeSat can send data at 200 gigabit per second using two wavelengths, each wavelength at 100 gigabit per second. And probably the most applied evidence is the use of Starlink for optical inter-satellite links. Each satellite of Starlink constellation is said to have 3 laser links that can reach 200 gigabit. which basically create a meshed network. And finally, you cannot forget about China. China recently made a significant demonstration of 100 gigabit per second satellite to ground laser communications. Note that both NASA and China are producing downlink demonstrations. Okay, I think I'm quite close to the end, but before closing this presentation, I would like to spend a few words about specification and standards. So NASA recently presented its first SDA version, which is Optical Communication Terminal Standard. This is with imprinting of the United States government, as you can imagine. ESA has issued the ESA specification for terabit per second optical links, a specification to which Sant'Anna has also contributed. And here you can see the first document sent to ITUT about the use of optical wireless in different application scenarios, not only optical wireless, of course. And finally, there is an activity also in ETSI, which is aiming at defining strategies for optical wireless communication for satellites. So with this, I come to the conclusion. I summarize what I hope I have transferred to you. That is, optical wireless communication is an emerging technology for very high-speed space links with complex system design. The design is far from being simple. I try to simplify it, but you can imagine it's not simple at all. Optical wireless communication for space can leverage upon existing devices and subsystems for fiber network with all the warnings that I gave to you. Still, you have a lot of technology that you can basically exploit with the limited cost. Of course, some key pieces are still missing and are under development. New solutions for some specific problems are still open and need to be investigated. But it's important to see that there is a strong attention of the industry and key users, which are already defining some specs. So this looks not just as promising technology, but something that can be reached within a realistic amount of time. So with that, I thank you for your kind attention, and any question is welcome. Thank you again.